My name is Davidson Matisse.
My name is Anthony Ryan. I'm the optimist of the group.
Ian Parker, I'm the spokesperson. I articulate the team's needs and stuff.
My name is Reagan Brown. I am the reporter. I maintain all the records and notes, meeting notes.
And I'm Niacin, and I'm the analyst for this group.
We are DARNI Development.
We are DARNI Development with our autonomous mower. And this is just kind of a breakdown of what we're going to be talking about today. So, get ready. All right, so keeping a well-maintenance lawn is very important to homeowners today, but with this comes a lot of accessibility issues. We want to, one, consider environmental conditions when it comes to, users being outside. It is projected that about 9,500 people receive skin cancer every year, and we want to, combat that. So an autonomous mower would be necessary to, keep people from outside as much as possible. Also, accessibility for those who are handicapped or disabled, giving them a voice-controlled autonomous mower would allow them to have more control and still, do their lawn as they wish, as well as being in such a society where we're always on the go. We want to have a little flexibility to be able to multitask. So there is a need for an affordable autonomous mower that has remote interface capabilities and gives consumers a safer option to keeping their lawn's maintenance, as well as being able to have control when they're not necessarily able to.
So our main objectives are, one, to incorporate voice recognition and communicate with the mower via a smart device such as Amazon's Alexa. Also, we want to focus on accessibility and ease of use, like Reagan was saying in the last slide, for people who may be handicapped. That would make mowing their lawn a lot easier. Next, we want a system with a reasonable battery life and an autonomous cell charging station. And lastly, we want to develop a gateway processor that provides wireless communication and interface to the mower hardware.
All right, I'm gonna break down the marketing requirements. First, I'm gonna hop down this second column here about a couple things that we want to hit in our design process. Like Naya said, the high battery life is definitely one of them. And the reason for this is our main goal. And the reason for this is it'll allow a lot more focus on the efficiency of the system, and that it wouldn't have to take as many breaks when doing mowing cycles. Some more, if you look at that third section, the system should have a battery that can endure extreme temperatures. So in the upcoming demonstration, you'll see that the possibility of the system overheating is something that we're going to be paying attention to going forward, and it overall will negatively impact the system. So we want to aim to have a system that can endure all types of situations, heat or cold. We want there to be an accessibility factor, and ease of use. So our idea is that down the line we'll be designing a graphical user interface, or GUI, that will display the modes of operation that the mower is currently in, upcoming tasks that it needs to handle, previous tasks, and any sort of diagnostic information that the user might need to understand the system that they're working with. We also plan on integrating a voice recognition component, possibly using something like Amazon Alexa, Google Home, Siri. There are a lot of staples on the market that we could use. Right now we're leaning towards Alexa. And what we want to be able to do is have the user control the system strictly through Alexa, telling it, hey, I want my lawn mowed tomorrow, or hold off tomorrow because I'm hearing it might rain, or cancel today's session. As simple as that. And moving forward,
Okay, so this is our level 0 block diagram. So as you can see, we chose mower voice command interface. And to the left side, you have your input, speech, and voice button. And to the right, we have our outputs, mowing schedule, mower state, operation, audio, and wireless data. So for the inputs, speech, we need the speech to perform or user to speak to the system to perform actions. Our voice button is also input, and that's for the user to press the button to start speaking to the system. For our outputs, mowing schedule, as Ian alluded to, you want to make sure you have the right times to pick when to cut the grass, when to, if it's raining, keep it, don't even use it. For our mower status, it updates the user on the progression of the grass cutting session, the operation, and that's just like the modes of the operation: audio, speech response, and wireless data. All right, this is our level 1 block diagram. So we have 3 blocks for this one. First one is a voice command. Then the inputs for that one is a voice signal, voice button. It outputs a command to the network interface. The network interface has an input to the wireless data. The wireless data is the input to the voice command. For our network interface, it has a input for a command signal that is also has an input for status. A mower control has outputs, mower schedule, mower state, operation, audio, and wireless data. This is this is our level 2. So we had to pick one level, one block diagram to go to our level 2. So we chose voice command. We have 2 blocks for the level 2 speaker and microphone. Its input is analog for the speaker. It outputs a audio input signal and the sound and goes into the microphone. Those will be the inputs for the microphone, and microphone outputs the audio audio output signal. And as you see, the level 1 block, it has the command as output, voice signal, and voice button as our inputs.
And this is our UML. We decided to go with a sequencing diagram just so that you can see the sequence in which the messages and signals are sent between the systems. We kind of wanted to do a very high-level view of the voice command, the network interface, as well as kind of the mower control and how that would be output into the function of the mower. So we started with the customer. We have our voice button, gives you an optional, to press just in case there is some sort of option button. Voice signal is the actual speaking of the customer. Once it goes through the voice command, we're going to have an audio input signal. This audio input signal goes through our Alexa ecosystem skill, and it will process through the skill and the ecosystem, it'll process our voice and send a call the AWS, which will assign us an intent, a service action to an intent. Through the AWS, which stands for Amazon Web Service Console, it'll go and connect to our cloud. Then it will make its decision, command a signal, send that to our mower, and then our mower will send out its operation, its function, and it'll send back a mowing state, a mowing status, our mower data, returning this response through the ecosystem, translating that back into text, and sending that out as far as a wireless status and a voice response back to our customer.
So along with all of that, we wanted to make sure that we have a system that could adhere to different type of temperatures, right? Or better yet, not overheat. So one of the tests that we decided to go with was the CPU temperature test, because you have a lot of data going back and forth. You want to see what's going to happen with all those data, because you do have a Raspberry Pi, and the Raspberry Pi has certain limitations. So came up with this test, CPU temperature test, which pretty much checks to see how hot the Raspberry Pi gets when running intensive programs. Furthermore, down the road, when I demonstrate the demo, you'll see that the temperature rises based on certain programs that is running. Some programs are more intensive than others, and while other programs don't require as much. So for this test document, one of the things that we did was write a script to perform the task pretty much, and take temperature measurement it will play a video and display that temperature and so forth. Or this is on the GPU end. On the CPU end, you have a very very intensive program that's running in the background, and that shows you the different temperatures in Celsius over time, like let's say about 30 seconds or a minute.
All right, so now we can talk about the money. Not the money we're gonna make, but the money we plan to spend. So the Raspberry Pi is pretty expensive. It's about $37, well, expensive for a college student. It's gonna be we're gonna need about 2 of them. So the total price is gonna be about $75. We're also looking at a USB microphone headset, a HDMI to VGA adapter, a Arduino board, SD storage card, and an SD formatter card, and also potentially a cooling fan discussed in the demonstration because of the heat of the system that we're going to be encountering.
This is also our work breakdown, just kind of giving you, day by day play on what should be happening and who's working on what. We start off with our Alexa interface, getting really comfortable with the ecosystem and learning how to work with it. We're going to have our advisor, our great advisor, Dr. Kelly, purchase our components. That's going to take about 5 days. Then we want to get used to the Alexa skill and test data and be able to implement Alexa-enabled interface through the Raspberry Pi. Naya and I will be working on that, and some of the resources we're going to use is the Flask Ask, the ngrok, and the Amazon developer tools. We will then want to simulate command, and a response, kind of like a hello world type situation. We want to test the updated skills and just get really comfortable with the Alexa ecosystem. Then we're going to go into the network interface, and Anthony is going to get really comfortable with, understanding how the network works. Download, install ngrok, download, install Flask Ask, and our resource is going to be our Raspberry Pi. Then Ian is going to go into research and development. He's going to work on communication protocol and figuring out, what needs to be said in order to get a response and an action. And then as far as the mower control, we're all going to be working on that and working on the communication between the Alexa skill and our mower and complete integration of the system.
So that was more of a detailed breakdown of the Gantt chart. So this is pretty much like our schedule that we that's pretty tentative as of right now, that we plan on moving forward starting in June, as we discussed. So everybody will start going into their internship and stuff like that. So we want to start around June the 2nd by just starting with the Alexa interface, purchasing components, giving you as much time as possible. But this could be earlier, and then with Alexa skill, the amount of days it's gonna take to just learn and be able to implement those, and then be able to simulate the commands and response with Echo. And with that, you want to also test those skill sets to see if it works. For the network interface, I'm just understanding the traffic and the research and everything that comes along with it. It takes about 39 days, I would tentatively, and then the more control. Being able to have the communication as Reagan stated, and that should hopefully take us 50 days. And this is from June to December. Also, yeah.
All right, and in conclusion, from the voice recognition feature that allows really easy to use interactive communication with the system, to the exceptional battery life, and the many sensors being used to provide for better navigation throughout cutting your lawn, we believe that our autonomous mower is a system that will provide groundbreaking ways to cut grass, and is a system that we believe people actually will want to use.
Question?
So if you could scroll back to the level 2. Yeah. So this and the UML need to be compared to one another, because I think they don't currently agree, and it's important that all of the things that you have agree. But I am really very pleased that your ability to take an existing system and begin to reverse engineer it. That's an important skill to have to do. Go to the schedule.
NAC chart?
Yeah, Gantt chart, right.
Gantt chart.
So this is something I will want you to continually refine and add detail to, because I have actually learned that for senior design, this is more important than almost anything else you will do. That if you don't have a schedule and you don't adhere to the schedule and you don't have formal conversations when a deadline is missed, then you won't get to where you want to with the project. You have a lot of things that you really want to do. I would also encourage, you have one test, and that's wonderful. I think building in time for those tests, and then time to, okay, it does get hot. They make heat sinks and fans. We need to find them, order them, get them, put them on, run the test again, see what the difference was after our redesign. Those are really awesome outcomes for you to have for your project. I want that for you. So when you look at your time, then understand that you need to give time for that. And you saw with just the one little one, it took you at least a week, right? Between the designing it, running it, finding out that there were things that could be fixed. And then you haven't done the second part yet, but it wouldn't take long once you had the parts. But I think that's really what makes you a 1% senior design. I mean, that's our goal, is to be in the top 1% of all senior design projects that have ever been done in ECE. So I think those kinds of things are really, really important to do. I love that you have well-defined roles and that there's a lot of parallelism here. I think that's a tribute to your ability to break down the project into its component parts and to work on them independently. Continue to communicate with one another, because a lot of what you have here is over the summer. And so you're gonna need to make sure that you also can do that. You have a demo.
Yes, I do. Yes.
Do we just leave it there?